Okay, welcome to the webinar on CO2 conversion into renewable fuels and chemicals. This webinar is organized by ECCSEL ERIC and ECCSELERATE in collaboration with Sotacarbo, OES, and SINTEF. Some recommendations just to start the webinar. All the participants must switch off their microphone and camera during the webinar, and questions will be welcome at the end of the presentations. So please type your questions in the question panel. Just a brief introduction of ECCSEL ERIC. ECCSEL ERIC is a European research infrastructure, which is conformed by the countries which are highlighted here in green. So we have UK, Norway, France, Netherlands, and Italy, which are the ECCSEL ERIC is providing open access to more than 80 world-class research facilities. And the main goal of the ECCSEL ERIC is to help industries and researchers to close CCU knowledge gaps, to contribute to reduction of CO2 emissions in accordance with the Paris Agreement. And the final goal is, of course, to reduce the global warming. This webinar is organized by the ECCSELERATE project managed by ECCSEL ERIC, where the aim is to increase use and long-term sustainability operation of the ECCSEL ERIC, developing marketing, access and service model for industries and SME, increase international collaborations, extending the activities from CCS to CO2 utilization, developing national laws and expanding the ECCSEL ERIC membership, and increasing the involvement of the ECCSEL ERIC in ongoing industrial CCS projects. The project also includes a capacity building programs with a series of webinar series like this one, dedicated to highlight some key topics on capture, transport, utilization, and storage. Some specific workshop held in conjunction with popular summer schools, and some tailored training course mainly addressed to attract industry and research and new user groups to the ECCSEL ERIC. So with this, I want to start. So today's agenda, we will have two keynote speakers, Angela Dibenedetto from the University of Bari and Alberto Pettinau from Sotacarbo. And I am Elvia Chavez, a research scientist from SINTEF Energy. So please, Angela, I will give you the floor.
Thank you very much, Elvia. I'm sharing. Can you see my screen? Can you hear me? I suppose yes. So thank you very much. Can I start? May I start?
Yes.
Yes. Yes.
Okay. Thank you. Thank you, Mr. Elvia, for your introduction. And let me thank the organizers for the kind invitation. This is just to introduce my organization. It is the Interuniversity Consortium on Chemical Reactivity and Catalysis that groups 18 universities, 73 research units. It is a no-profit public organization of excellence in research, recognized in 2002 by the Ministry of the University and Research. My research group deals with the valorization of spent carbon, either carbon dioxide and residual biomass. And here I have selected some papers and books published on these fields. My talk today will deal with the transition from linear carbon economy to circular carbon economy. I will discuss the effect of the linear carbon economy and the need to develop technologies for the conversion of large volumes of spent carbon into working carbon, considering either the direct conversion of CO2 or the utilization of biomass. I will shortly discuss the photochemistry considering for CO2 conversion, and also the integration of catalysis and biotechnology. As we know, humans have developed a linear concept based on few words: take, make, use, and dispose fossil carbon. The existing technology are very low in efficiency, and almost 70% of the chemical energy is released in the atmosphere as thermal energy. The emission of carbon dioxide is around 35 gigatons per year, and almost 85% of energy derived from fossil carbon. So there is an urgent need to reduce the CO2 emission and energy and its accumulation in the atmosphere. It can be done either introducing efficient technologies able to reduce the use of fossil carbon, or using perennial or renewable primary sources. For being used, carbon dioxide must be captured from continuous or concentrated point sources, such as power plants or industry, or directly from the atmosphere, and it can be disposed in natural field, considering the CCS options, or used for several purposes, applying the concept of carbon capture and utilization. CCU differs from prevalent carbon capture and storage solutions in one basic way. CCS captures CO2 emissions exclusively for storage, usually reinjecting them into geological formation. The goal of CCU is conversely the conversion of carbon dioxide into valuable chemicals. So carbon capture and utilization can be considered as a way to complement the natural carbon cycle, and also a way for the transition from the linear to circular carbon economy. And in a circular economy view, carbon dioxide is considered by the chemical industry not anymore as a waste, but as a building block or a source of carbon. And in some cases, CO2 is used to produce chemicals at commercial level. In fact, several efforts have been done in order to obtain carboxylates, carbonates, and carbamates, reacting CO2 with olefins, dienes, alkenes, alcohols, and so on. Of course, the process are all catalytic process, and some of them are endoergonic, so it's not easy to implement this kind of process. And so one can implement the direct conversion of carbon dioxide, or may couple what nature do, that is able to fix a large amount of carbon dioxide, and use chemistry to convert biomass into chemicals, materials, and fuels. Also very interesting is the integration of chemistry and biotechnology. Whatever we do, we have to face the issue of one extra oxygen atom. And this holds when we substitute hydrocarbons to carbohydrates or CO2 to CO. Of course, we need to develop new catalysts for different catalytic processes. And the CCU concept has the potential to shift the way we consider carbon dioxide. Till recently, carbon dioxide was considered exclusively as a waste. Now we start to consider it as a source of carbon for the synthesis of fine chemicals, bulk chemicals, materials, and so on. And it has several benefits and may contribute to the development of a carbon dioxide water economy. For detail about this, you can consider to see the book published by Professor Aresta and colleagues. The table here gives the actual use of carbon dioxide in the synthesis of chemicals and the perspective use at 2030, calculated considering the expected market growth for the listed chemicals, and assuming that the new technologies will be able to convert large volumes of CO2. Of course, when we speak in terms of CO2 chemistry, we have to consider the thermodynamics. The figure here shows the Gibbs free energy of formation of several C1 species, and as you can see, it is quite evident that when the oxidation state of the carbon atom remains around 4, as in CO2, the reaction may be exergonic. Conversely, when it is reduced from +4 to +2 or lower, a significant amount of energy is needed together with hydrogen. So, and this is the key point. The question is where and how to get hydrogen. So we can divide the reaction for CO2 conversion in two main classes. In the low energy processes which are on stream, and the high energy processes that are under investigation. And if cheap hydrogen generated from water using perennial energy will be available, the reaction depicted in the right part of the slide will be exploited with a large contribution to carbon recycling. So now I will discuss some processes that convert CO2 into chemicals, each having a market, a quite large market. Is the case of dialkyl carbonates, either linear or cyclic, that finds utilization applications in several fields, such as solvents and reagents, pesticides, drugs, cosmetics, polymers, and also very recently as additives to gasoline. The synthesis is, as you can see in the upper part of the slide, the reaction is an example of sustainable process. The atom economy is high, the only co-product is water. But the problem here is that at the equilibrium concentration of the formed carbonate is quite low, often is around 1% or even less, depending from the reaction conditions. Another drawback is the formation of water that shift the equilibrium to the right, and also may deactivate the catalyst and also the carbonate during its formation. So water should be eliminated in order to shift the equilibrium to the right. Several solutions have been proposed, such as the use of inorganic organic traps or membrane reactors, and very recently we have propose the use of pervaporation membranes. In fact, we have set up a flow system where pervaporation membrane have been inserted during the cycle, and which the pervaporation membrane is able to reduce the amount of water in the reaction mixture, increasing the conversion of into carbonate. Interesting is the use of urea is the use of carbon dioxide in the form of urea. In fact, urea can be considered as an active form of CO2, and has been used for the synthesis of carbonate, either linear or cyclic, as you can see in this slide. The reaction mechanism has been studied in detail by several groups, but further investigation are still in progress for better understanding the potential of such methodology that requires the recovery of the ammonia in order to reach an economic acceptation. What we have to say is that with urea we observe a better thermodynamic, higher conversion, as the reaction is not equilibrium driven. So considering the forecast, have been calculated that the amount of carbon dioxide needed is low with respect to the amount of carbon dioxide available to use. So in order to change the direction, we have to consider the possibility to use different source of energy, such as, for example, sun and wind, which are available and also are at low cost. We need to develop a system able to store this kind of energy, solar and wind energy, into chemical bonds. At the moment, we are the high energy processes for CO2 reduction are feasible with the use of non-fossil carbon-based energy sources, and so chemists have to take this opportunity. This aspect has been discussed in detail in this book published this year by me and Professor Aresta. Photocatalysis can be useful. In fact, photocatalysis coupled to the use of solar energy may offer interesting perspective in this area, and recently we have studied the direct insertion of CO2 into CH bond of acetyl acetone to effort valuable chemicals. Interesting is also the photoreduction of CO2 in glycerol or isopropanol water by using semiconductors. And very interesting is also the hybrid bio-inspired system used for the enzymatic reduction of CO2 to effort methanol in water. This process combines two processes. One is driven by enzymes, dehydrogenases, and the second is driven by a semiconductor, so photocatalyst. The enzymes are able to convert CO2 into methanol, while photocatalyst is required in order to recover NAD+ and reconvert it into NADH, which is required by the enzymes. So an interesting approach is what we have already said. Let nature fix CO2, and nature is able to fix a large amount of CO2, and then chemistry may convert biomass. So what is interesting is the integration of biotechnology and catalysis, as catalysis can be considered as a tool for accelerating bioprocesses, and so the bioelectrochemical systems can be used to provide hydrogen for carbon dioxide conversion into valuable molecules. And if we consider the fixation of CO2 into aquatic biomass, for example, microalgae, we can consider applying the concept of biorefinery, that biomass can be used to obtain a variety of molecules, materials, and also fuels. And if biodiesel is obtained, and together with biodiesel is obtained also glycerol, this latter can be converted into other molecules of interest, of industrial interest. In this case, glycerol is reacted with CO2 or with urea to effort oxazolidinones, which is a new monomers for the synthesis of polyurethanes. We have studied the effect of temperature and the different behavior when CO2 is used or urea. Moreover, glycerol can be converted into 1,3-propandiol using a biotechnological approach, and then 1,3-propandiol by using catalyst, particular mixed oxides as catalyst, can be converted into 1,3-methylene carbonate, which is biodegradable materials, polymer can be used to produce polymers or film and coating materials. And so this is another example of integration of biotechnology and catalysis. Very interesting is also the combination of microbial hydrolysis of cellulosic material to C5 and C6 fractions with catalytic conversion of them into new monomers. For example, in this case, either C5 fraction or C6 fraction can be converted into furan dicarboxylic acid, which is a new monomer for the synthesis of polyethylene furanoate, polymers with interesting properties. Just to consider a final example, the bioelectrochemical systems are very interesting because in this kind of system, bacteria interacts with solid state electrodes by exchanging electrons with them, either directly or via redox mediators, and allow the conversion of carbon dioxide into carboxylic acid, alcohols, formic acid, and energy products. So in conclusion, CO2 is a valuable source of carbon. It is already used in the chemical industry at a rate of 200 million tons per year. Using the existing knowledge, the forecast is to increase the amount of CO2 used by 370 million tons per year. Very interesting is that the nature makes from CO2 1,000 energy-rich compounds using solar energy. So the combination of the use of solar energy with CO2 catalytic conversion may bring to the reduction to fuel, enlarging the utilization to a several gigaton per year level. And very interesting is the approach of the hybrid catalysis and the biotech that may open a new scenario in CO2 conversion into chemicals, materials, and energy products. Let me cite some activities related to CO2 and biomass valorization at the national level within the consortium on Inter-University Consortium on Activity and Catalysis, but also within the bioeconomy group and the RUCADI group, the Recovery and Utilization of Carbon Dioxide group. And also at the international level, the very new formation of the Just Transition Platform Working Group on chemicals. The first meeting will be on November 18, but also activity within the Italian cluster of green chemistry, and also the activity related to the organization of the International Conference on Carbon Dioxide Utilization, where I have the vice chair. I am the vice chair. The next will be in the USA at Princeton University in June-July 2022. I would like to thank my research group and you for the kind attention. Thank you very much.
Yeah, thank you a lot, Angela. It was very interesting. So let's please start the presentation of Alberto Pettinau. Alberto, the floor is yours.
Do you hear me?
Yes.
Yes.
Okay. I assume you see my presentation?
Yeah.
Right? Okay, that's perfect. Thank you, Elvia. So basically, my presentation is, of course, complementary with the Angela's one. So her presentation was focused on CO2 conversion into chemicals, and my presentation is focused on CO2 conversion into green fuels. So let me start with this slide. So it's a sentence mentioned just a few years ago by George Olah, a Nobel laureate in 1994, who proposed the so-called methanol economy. So he said, we do not believe that there will be a single solution to the discussed global problems. However, the approach of the chemical recycling of carbon dioxide to produce carbon neutral renewable fuels and materials offers a feasible and powerful new alternative and is entering in the stage of gradual practical implementation. I choose this sentence because it gives a general idea on the importance, on the strategic importance on the use of CO2 as I can say as raw material for the production of renewable fuels. So let me spend just half a minute to introduce Sotacarbo, which is a company owned by Enea and the regional government of Sardinia. And our activities are focused on low carbon technologies, basically biomass and waste gasification, CO2 capture, utilization and storage, and energy efficiency. So we have we are partners of IEA, International Center for Sustainable Carbon and Greenhouse Gas Program. Several of our infrastructures are part of the ECCSEL ERIC facilities. We represent Italy in the European set plan, in particular in the working group on CCUS, and we are one of the founding members of CO2 Value Europe International Association. So just to quickly introduce Sotacarbo. So e-fuels towards climate neutrality. So basically, in Europe, we have every year a little bit less than 500 terawatt-hour of renewable electricity, which is wasted because of the impossibility at the moment to store a big amount of electricity. So it involves an instability of the electric grid. It's a limit for a further diffusion of renewable energy sources. And probably the most important problem, it needs the use of fossil fuels power generation plants as a hot reserve to provide, to supply electricity when the renewable energy is lower than the instant demand. So that's the reason why this very large amount of electricity is wasted every year. So it means basically more or less 150 medium-scale power generation plants. So it's the same amount of energy wasted every year, basically 13% of the European energy demand. So how to solve this problem? Basically, the approach to store energy are mainly three. So batteries, but they are characterized by high cost, limited capacity, and environmental impact. So their application, for example, is efficient for transport, for light transport, basically cars, and other specific applications. Hydroelectric, but most of the potential is already developed. So there is a relatively low margin for new plants. And the other possibility is a chemical energy storage. So in terms of, so this approach has a very, very high potential development. So this is I can say a quite strange slide, considering that one of the approach proposed for the decarbonization of Europe is hydrogen production. But there is a problem. Basically, hydrogen needs renewable electricity and water. But where the renewable electricity is available, water is not so easy so the availability of water is limited. And on the other hand, where water is widely available, renewable energy, mainly from wind and sun, is limited. So basically, one of the proposed approach is the production in North Africa, long pipeline for hydrogen transport to Northern Europe, where the energy is required, but it has never been done before, considering a long pipeline for hydrogen transport. Big storage sites are required, but also this technology is not mature from the commercial point of view. And the industry that should use hydrogen, they are not ready for this kind of approach. The alternative is ammonia, which is easier to be transported than hydrogen, but it's toxic and explosive. So CO2 derived fuels can be an alternative option. So how can we define e-fuels? So basically, the definition is very, very easy. Liquid or gaseous fuels produced not from fossil sources, but from renewable electricity, from renewable electrical energy. So basically, hydrogen can be considered as an e-fuels, of course, if produced from renewable energy, but also mixing hydrogen with CO2, it is possible to produce methanol, dimethyl ether, methane, and also a sort of synthetic oil with the other products conventionally produced by fossil fuels, so diesel, gasoline, etc. All these fuels can be produced also from green hydrogen and carbon dioxide. So basically, why we can consider e-fuels as a renewable fuel. So it doesn't matter if CO2 is captured from fossil fuel plants, bioenergy plants, or directly from air. The key point is that hydrogen is produced from renewables. Basically, we can use CO2 mixed with hydrogen for the production of this kind of e-fuels. So why they are very promising for industrial applications? So basically, it is a key, as I mentioned, for storing electricity. This kind of fuels can allow the decarbonization of the so-called hard-to-abate sectors, for example, heavy transport or industry. Just to give you an example, we are discussing with a company which has big ovens for the treatment of specific materials. These ovens work for just few days per week, so the capture of CO2 is not convenient. So they basically use the LPG as a fuel. So it's very difficult to remove CO2 from the flue gases. Very difficult, mainly from economic point of view. It's easier to feed these ovens directly with e-fuels, with renewable fuels. So this approach allows the decarbonization of several industrial sectors. Several technologies are already mature. I will give you a few examples in the next slides. And as we see later, these kinds of fuels are starting to be competitive from the economic point of view. So this is probably the most important example of renewable fuels plant. So this is the Georgiola renewable methanol plant, installed in 2011 near Reykjavik in Iceland and owned by Carbon Recycling International. It operates since 2011. They produce methanol, which is commercialized with the name of Vulcanol, considering that they take CO2 from the underground. It's a natural emission of CO2, and they have geothermal electricity for hydrogen production. So this is very efficient unit, which is probably the most interesting example of this kind of application. And for example, can be used for the decarbonization of the transport sector. The picture represents one of the most relevant examples. It is the Stena Germanica ferry, owned by the Stena Line, the Swedish company Stena Line. They modify the engine for refilling with the renewable methanol. So this ferry works with a renewable methanol as a fuel, and the international market of methanol is growing significantly in the last few years. And this is another application, another existing plant operating since 2013 in Germany and owned by Audi. They produce methane from green hydrogen and CO2. So just to give you an example of a specific application. And this is probably the weakest aspect of this technology. So the energy balance. Here, this is a study published by the International Energy Agency a couple of years ago, referred to methanol, methane, and in general liquid power to liquids, which means basically gasoline, diesel, etc. So basically, here you can see that there is a significant energy losses for hydrogen production, and a further loss for the final conversion of green hydrogen into renewable fuels. So basically, more or less 50% of the energy is wasted through this process. But so this is just a general consideration on the cost. So currently, CO2 derivatives are 2 to 7 times more expensive than the fossil-based counterparts, where the cost of electricity accounts for 40 to 70% of the whole production cost. But the key advantage is a significant reduction of CO2 emissions. This evaluation is based on a life cycle assessment, so considering the whole technology from the cradle to the grave. So it's basically a cradle to grave approach. So this is another evaluation published by the International Energy Agency. So this is a comparison between the current and the future cost of this approach. So the most significant case is the central one referred to methanol. So in the near term, methanol production costs, so the fossil-based methanol is significantly cheaper. So it's the current price is the dot at more or less $350 per ton. The renewable one is more expensive. In the diagram, it's more than $200 per megawatt hour, or more exactly, between 120 to $210 per megawatt hour. So the variation depends on the CO2 feedstock cost, whereas the market price, the current market price is a little bit more than $50 per megawatt hour. But the long-term development of this technology, mainly the wide diffusion of this technology, will allow very significant reduction of this cost, which should become competitive with the current technologies, considering that the CO2 emission permits will involve. So basically, the European emission trading scheme, the renewed emission trading scheme, will involve an increasing of the fossil-derived methanol. So this is just a hint about the so-called Fit for 55 policy, the climate package from the European Union, which aims to promote the development of this kind of fuel, in particular with the so-called Refuel EU for aviation and for maritime, that these directives will define very specific targets for the diffusion of e-fuels, and the restrictions are specific for the fuel suppliers, not to the airlines, in order to assure the competitiveness of all the different kinds of approaches and different kinds of fuels. There is a public consultation in progress, and the package should be approved at the end of this year. So let me spend just one more minute to introduce the ECCSEL ERIC facilities on carbon capture and utilization. So this is just a list, just to give you an idea that within the consortium there are several facilities on specifically focused on research on CCU. And so this is one of the ECCSEL facilities installed in our research center in Sardinia, Italy. This is basically a X2-liquids bench scale unit that allows, for example, detailed catalyst characterization. So it's a unit characterized by a very wide flexibility in terms of pressure, temperature, and in general operating conditions. And we are using this unit for the characterization of catalysts for CO2 conversion into fuels. And this is probably the most relevant result. It's a specific catalyst developed in our research center, characterized by a very high efficiency, stability, tolerance to oxygen, and in particular, probably the most relevant property of this material, it doesn't need any pretreatment, any activation procedure. And this is a new plant which is currently under construction. It should be available at the beginning of next year for the development of basically it's the same technology, so CO2 hydrogenation into methanol, dimethyl ether, or methane. So it's a pilot unit, so designed for the production of more or less 5 kilograms per hour of product, equipped with 2 different reactors for different kinds of process applications. So thank you very much for your attention. Of course, every question, I'm pleased to reply to questions.
Yes, thank you a lot, Alberto. It was very interesting. And maybe to follow up with the questions, maybe we can ask Angela to switch on the camera. And for the participants, you can use the question panel, or you can unmute yourself and ask any questions if you have. In the meantime, I can ask some questions maybe. Angela, it was very nice what you presented. I think it was kind of an overview on the chemical production from CO2. One of the questions that I don't know if you have some kind of thinkings about this. You mentioned about using solar energy for the photocatalyst process. What are the views on the large scale implementation for this kind of technology? Because it looks quite promising, but it can be very challenging for large scale implementation.
Oh, thank you for the question. The proposal to use solar fuel is and CO2 conversion is at lab scale. So we need to find the right catalyst to convert CO2 in this kind of process. I hope that the research group interested in this kind of development, of this kind of topics, will be able to find robust catalyst, and particular photocatalyst to able to convert CO2 into chemicals or energy products in general.
Yeah, but I understand. I mean that to kind of increase the or to accelerate the process, one must expect that when it's a huge area, you know, in order to have more kind of some interaction with the solvent or something like this.
Sorry, I cannot hear you.
Yeah, I was just saying that probably one of the constraints about the solar energy is the area of reaction. You know, if you want to accelerate the process, probably you need to increase the area of reaction.
Yeah.
Then the applications probably then they are limited by this.
Yeah.
But yeah, we have one question from the audience. The question I can read maybe, just 1 second. Yeah, so the question is for Alberto Pettinau. Is the catalytic reactor for methanol production sensitive to contaminants present in the CO2 stream? For example, trace of mercurio or acid sulfuric or ammonia or methane. Hey, you're mute, Alberto.
Sorry. Thank you for the question. Basically, it strongly depends on the catalyst. So basically, most of the catalysts, I can say all the catalysts are poisoned by this kind of materials, and of course, several of these contaminants are specific for the capture process. So, for example, if CO2 is captured from I don't know, for example, the problem with there can be problems with mercury or with sulfur oxides, or also oxygen, considering the high oxygen concentration in the flue gas. So of course, in these cases, the pollutants can can reduce the efficiency of the catalyst. Also, oxygen is one of them of the key. I can say one of the key contaminants for this kind of process, considering that oxygen typically deactivate the conventional, the commercial catalyst for this kind of processes. So there is a need to purify CO2 to avoid the problems with the catalyst. So to reduce to shorten the life of the catalyst.
Yes, yeah, there is another question from David to Alberto. You showed a nice graph from the IEA concerning the long-term price of methanol produced from CO2. In your opinion, what is going to be the impact of the catalyst cost for future mass conversion of CO2?
The question is very interesting. The answer is very difficult, considering that so at the moment catalyst is basically the impact of catalyst in the general cost of e-fuels production depends not specifically from the cost of the material, but from the efficiency of the whole process. So basically, the efficiency is limited by thermodynamic properties, so by the thermodynamics of the process. So basically, the margin to optimize the process is relatively limited. So there is a margin, but I don't expect that the catalyst can play a very important role from this specific point of view. But of course, for example, the catalyst I mentioned, the material we have developed in our labs, we have patented, for example, allows to work without any pretreatment. So this can involve a significant reduction of cost, and also the tolerance. So the key, probably the key aspect is the tolerance with pollutants. So not specifically the conversion efficiency of the material, but the tolerance and the operation of the whole process. So these are the key aspects for to reduce the cost of the conversion, the production cost of methanol, the milliliter, etc.
Yes, but yeah, probably. I mean, after about the tolerance, I mean, to transport the CO2, we have to remove some of the other gases. So yeah, probably at the end, what you get is already without these other gases. Yeah, but yeah, very interesting question. Any more questions from the audience? If not, then I think it's 3 o'clock, and we can close the webinar. Thank you, Alberto and Angela, for their presentations. And thank you to the audience for participating in this webinar.
Thank you to you for chair the session, and all of you to participate. Bye-bye.
Yeah. Thank you a lot. Bye bye.
Thank you.